Calculus Math 11. Dots. Dots. Trigonometry Addendum. Special Triangles. Now, although every right triangle is distinct, there are two that we refer to as being special triangles. These are the 45-45-90 and the 30-60-90 triangles. The 45-45-90 is an isosceles triangle. Essentially, it's the triangle formed by drawing the diagonal across a square. Now, the equal sides could be any length, but to keep it simple, we'll give them a length of 1 unit each. And how can we calculate the length of the hypotenuse here? Well, by using the theorem associated with everyone's favorite ancient Greek mathematician, Pythagoras. So, when we do that, we get a squared plus b squared equals c squared, giving us 1 squared plus 1 squared equals c squared. And if we calculate this, we get c is equal to the square root of 2. Now, if we go ahead and look at the trig ratios for this triangle, we get the sine of 45 is 1 over root 2, the cosine of 45 is 1 over root 2, and the tangent of 45 is 1. The other triangle that we'll look at is the 30-60-90. This triangle is 1/2 of an equilateral triangle, where we drop a perpendicular from the top vertex down to the base. This will bisect the 60-degree angle at the top, and also bisect the base. The hypotenuse must be twice the length of the base. And so, to avoid using fractions, we can label those two sides with lengths of 1 and 2. As before, we can use the Pythagorean theorem to solve the third side, going 1 squared plus b squared is equal to 2 squared, and ending up with b is equal to root 3. Be careful when using this triangle to remember that 2 is greater than the square root of 3, and that 2 is the hypotenuse, not root 3. When you calculate the trig ratios for this triangle, you will get the sine of 60 is root 3 over 2, the cosine of 60 is 1 over 2, and the tangent of 60 is root 3. We'll also get the sine of 30 is 1/2, cosine of 30 is root 3 over 2, and the tangent of 30 degrees is 1 over root 3. Something else here to notice is that the sine of 30 and the cosine of 60 are equal. And this isn't just true in this special triangle. This is actually something that's true for any two angles that add up to 90 degrees. So without calculating, I can say with confidence that the sine of 70 is equal to the cosine of 20. And the sine of 10 is equal to the cosine of 80, etc. Now, the special triangles can be used in the following way. Give the exact trig ratios for an angle of 210 degrees in standard position. So if we consider drawing a sketch of this angle in standard position, we can also consider and see quite clearly that the reference angle, located here, is just 30 degrees. So essentially, we're just calculating the trig ratios for a 30-60-90 triangle. If we mark in the side lengths on this 30-60-90 triangle here, we can easily calculate the trig ratio. One thing to be careful with is that these lengths aren't just 1 and root 3, but since they're off to the left and down on the y-axis, they are -1, negative root 3, but this length is still just 2. The sine of 210 -1 over 2. The cos of 210 is negative root 3 over 2. And the tangent of 210 is -1 over negative root 3, which is really just positive 1 over root 3. Double check with your calculator if you like. One reason that we like these special triangles so much is that we can work with exact values rather than decimal approximations. We don't even need a calculator. The question often comes up, how many decimal places should I use? Well, all of them, really. That's a quick reminder of properties with special triangles. My advice? Anytime you're doing a page of trigonometry questions, draw these two triangles somewhere at the top for quick reference. And I would do the same with a test or a quiz. Well, that's all for now. Until next time, keep your pencils sharp, and I'll see you in class.